called the only Debye theory is able to explain this one. And this region is essentially Dulong Petit. So these are dominant uh, specific behaviors of crystalline solids. Now, if you remember, the model that we have been following is essentially kind of a spring block model, where the bonds are modeled as springs and atoms or molecules are modeled as blocks. So spring block model is, just to recall, that you have these blocks and these represent atoms, and then the bonds between them are represented by springs. Okay, so I'm just writing some representative number of atoms, and you have a model like this. Now thermal energy, when it is imparted to the system, all these springs get expanded and contracted, and that results in oscillations of atoms, and these oscillations can be in normal coordinates, can be written as a collection of harmonic oscillators. So Boltzmann considered a set of classical harmonic oscillators in deriving Dulong-Petit's law, and Einstein considered each of these oscillator can absorb or emit energies in discrete quanta, so their energy levels are discrete. So using these two things, we have seen already in the past lectures that how Dulong-Petit and Einstein's theory could be derived. Now, at very low temperature, what happens is that there is not enough energy to excite individual atoms. For example, let's consider this situation. Let's say consider a one-dimensional 1D lattice. Okay, so let's say that we have a block, spring, a block, and a spring like this. Okay, so let's say there are so many number of them, and lead this ends. Okay, so this is a one-dimensional lattice. Now there can be there are two kinds of excitations. So the excitations can be categorized into what is called an extended, I do not remember what is the correct word for this, extended or delocalized excitation, or you can have a local excitation. Okay, so the difference between these two is something like this. An extended excitation is something like you have an atom like this, and then the next atom is a little bit going up like this, going down like this. So this is a long, what is called a long range excitation, in the sense there are many particles, many atoms are deviating from their position, but they are deviating by little amount, such that there is an excitation of this type. And then local excitation is something like this. you have, let's say, all these things are like this, but let's say there is one atom here or two atoms here which are excited. So this is basically a local event. That means these things are not disturbed much. Now it's probably intuitively easy to understand that uh, these kind of excitations, that means delocalized excitations, are low energy excitations. They are lower energy excitations, or they require lower energy compared to local excitations. Compared to this, they require lower energy compared to this kind of excitations. So when at very low temperature, so because of that, at low temperatures, since we don't have too much of energy, at low temperatures, okay, it is these what is called extended excitations that take the energy or absorb the energy in that, take or absorb energy. So this basically tells you that you have, so now this entire lattice is you have to treat it like a continuum. It is like a string, vibrating string like thing, and this kind of oscillations you can actually describe in terms of normal modes of oscillations. Okay, so now you can see that the frequency of these oscillations, are somewhat continuous, or it can be treated to be very continuous in thermodynamic limit. For example, I want you to recall, maybe you have studied this already in your other courses like solid state physics, that if you have these lattice vibrations, okay, so when you study these lattice vibrations, you might have studied a kind of a dispersion relation, which is something like this. Let's say you have k in this direction and omega of k. Okay, so then you see that there is some kind of, let's say this particular point is here pi by a, that is the edge of the Brillouin zone. Then you are going to have a dispersion relation, which is something like this. Essentially, this dispersion relation means that it's not that they are continuous. It's not that it's a continuous curve. There are different frequencies. Okay, so you may try to represent this as a curve like this, because I'm sure you remember that this expression is some modulus of sine k, something like that, right? That dispersion relation. Now The exact dispersion relation is not very important for me, but I want you to understand that this. So all these frequencies which are on this curve, okay. So let's say I say this is a point. That means this is a particular frequency, and a lattice vibration of this frequency is allowed. Okay. Now this is completely a classical statement that you have different frequencies allowed, and each frequency is like a normal mode frequency, and the frequency will have a dependence on the wave vector, and omega of k is called the dispersion relation. So this is called dispersion relation. By the way, I think this particular curve is called acoustic branch. Acoustic branch. Okay, so this is just a name because it's like a sound wave. Because when you go to omega versus k, when k is close to 0, this omega is almost proportional to k. So omega is proportional to k is the kind of acoustic behavior.
Sir,
Yes.
for monoatomic lattice, do we have acoustic branch? Like for I read that for diatomic lattice, like there are two more than one atoms in
Yeah.
the lattice. There will be optical branch and acoustic branch.
Yeah.
But for
Yeah.
monoatomic lattice, there is no acoustic branch, I think.
No, I think that's not correct. No optic branch, but acoustic branch is there for everything.
Okay, sir.
Yeah, optic
Okay,
branch will not be there.
okay, thank you, sir.
So now I want you to realize that suppose if I, so now this is just a lattice vibration. Now the quantization business is something like this. Okay, so I want you to realize that let me draw this picture again with slightly a bigger size. So let's say this is omega of k, and I have the Brillouin zone boundary somewhere here, and then I have, let's say, different frequencies which are like this. These are some discrete different frequencies. Maybe they are closely spaced, and I am drawing them differently to differentiate them clearly. So the same picture I have drawn it here in terms of points. So this is like, now suppose if you take this particular point, I mean this particular frequency, it is a lattice vibration of that frequency. Now you can quantize that one. So suppose if I take this frequency and this vibration, okay, if you quantize this vibration, that means now you must imagine thinking of a harmonic oscillator of that frequency, okay, of this frequency. Then you are going to have discrete energy levels. That means energy to that vibration will be taken in terms of h bar omega by 2, 3 by 2 h bar omega by 2, and so on. And suppose if you take another frequency, then you can have another harmonic oscillator associated with that, and there are corresponding discrete energy levels. Now, an excitation where an energy which is equal to a quantized energy corresponding to a frequency, such an excitation is what we call as a phonon. Okay, phonon is essentially called a quantized lattice vibration or quantized uh, sound wave. So you can see that means each of this frequency can now be treated as a quantum harmonic oscillator, and that has discrete energy spectrum. So a phonon is an excitation corresponding to one of these allowed quantum mechanical energy levels of an allowed frequency in the acoustic branch or optic branch. In this particular case, I am talking about one branch. So whichever branch, then you are going to have this quantum mechanical energy levels associated with that. and if you have an excitation which corresponds to that frequency, that is called a phonon. Now, the advantage of this way of quantization is very useful, because once you say that you have this phonons, okay, then you can actually think of so once you say that, so now you have a lattice and you have lattice vibrations, and then you quantize them, then this entire thing can now be considered as a gas of phonons. Okay, so now you have to simply understand what this phonon is and what this gas of phonons is. Now, a phonon is like a photon. So phonon has no chemical potential, in the sense you can create a phonon or destroy a phonon by without any cost in the energy. So first property of the phonon is somewhat similar to photon, is mu is equal to 0 for phonons, and phonons like photons are also massless. Okay, mu is equal to 0 for phonons. This the chemical potential is equal to 0, and um, and phonons, of course, you might have recognized by now that we are studying under Bose Einstein statistics. They are bosons. Okay. Now, if we understand this, then we have to ask a question that at low temperature, these are the phonons that are getting excited. That means basically these collective excitations. That is the, I think, uh, the word which I was saying that I am not remembering is that these are called collective excitations. Collective excitations, and this is essentially called a single particle excitation. Single particle, I mean that it can be a few particles also. Single particle excitation. So single particle excitations require higher energy than the collective excitations. So in collective excitation, these collective excitations are the ones which are most likely to be excited when your temperatures are very small. So we should be able to understand how these collective excitations take the energy, and that will tell us that will give us some information about the specific heat. So Debye theory has the following inputs. So just like so let us look at Debye theory, not the way Debye has done it, but the way we would like to do it after having so much of understanding of Bose-Einstein statistics and so on. So one of the inputs that we have is the average number of phonons. Okay, so let's say that energy of the phonon is h bar omega. Okay, this is essentially same as h nu, because this is same as h nu. That is what we used in photons case when we discussed Bose work. So I divide by 2 pi and multiplied by 2 pi. 2 pi nu is omega and h by 2 pi is h cross. So this is same as that. The energy of the phonon is h cross by omega. Now you talk about density, density of states, or it is basically density of phonon density of states. which is essentially the number of normal modes in the range between omega and omega plus d omega. This is what is your, this is not the density of states. So to define the density of states, we have to say this is equal to density of, maybe you call them as density of modes into d omega. Okay, so this is one important quantity that we would like to have. And Debye has used Rayleigh's expression, so or whatever expression that we have used in the Bose case. So for photons, we have this g of nu to be 8 pi nu square by c cube. Okay, so let's try to represent put it in the, so you know this nu is equal to omega by 2 pi. So we can get this g of omega is equal to 8 pi omega square divided by c cube into 4 pi square. So that gives you 2 omega square divided by pi c cube. Okay, this is just for the expression for photons is just recast in terms of omega. But notice that we have for every frequency, for every omega, we can have one longitudinal vibration and two transverse vibrations, because once you fix the direction of propagation, then there can be two directions, transverse vibrations. And in general, the velocities of these propagations can be different. Okay, so let's say that the longitudinal vibration has got a velocity CL and transverse vibration has got a velocity CT, and these are two in number, and this is one in number. So the density of modes for phonons can be now written as g of omega is equal to 2 omega square by pi c, oh sorry, this 8 also involves, remember this 8 involves the two polarization directions, right? So we don't want to have polarization, so let us keep, because we will keep this 4, in which case this is simply omega square by pi c cube. Now for transverse, because there are two of them, I will write 2 and then ct cube plus omega square divided by pi cl cube into d omega. G of omega d omega is equal to this, and this is what is given by the number of modes in this region. Okay, so this is the density of modes, and once we have this density of modes, then we can say that if total number, okay, the total number, so let n be the total number of atoms, okay, which is of course is equal to the total. In terms of when you decouple the oscillators, the total number of oscillators will also turn out to be this, and then the number of normal mode frequencies will also be same as this n. So this implies that your integral g of omega d omega, okay, and when you integrate this from 0 to infinity, for example, okay, you should get this to be the total n. So you should get this to be n. But then Debye has assumed that there is some kind of a cutoff frequency, which he called as Debye frequency, and he said up to this, if you integrate, that is enough, you will get n. That means these frequencies cannot be very high, and there is some particular cutoff frequency. So this omega d is called Debye cutoff frequency.
Excuse me, sir.
Yes.
Sir, in case of photons, you have taken two state of polarization, right?
Correct.
But in case of phonons, you are taking two longitudinal and one transverse. So how will you discriminate this? How will you understand this uh, photon and phonon cases?
Yeah, in photon case, there is no longitudinal vibration, because if electromagnetic wave is, let's say, electromagnetic wave, uh, the description is same both in the case of electromagnetic wave and photon. So if the photon is electromagnetic wave is passing, let's say, along z direction, then there is no oscillation in that direction. There's only movement in that direction. The oscillation is always in two directions perpendicular to that. Okay, so there are two polarizations. Polarization is defined as the direction in which electric field is oscillating, and that is there can be two linearly independent orthogonal directions for the oscillations of the electric field. So the longitudinal part is absent, that's all. For phonon, you can have a longitudinal part.
Okay, sir. Okay, sir.
Yeah.
Okay, sir. Thank you.
So now you can see that this means that you have, let us write down this 2 divided by pi ct cube plus 1 divided by pi cl cube into integral 0 to omega d, and omega square d omega is equal to n. So this gives you that this is omega cube by 3 and omega d cube. Okay, so this is this particular factor into omega d cube divided by 3 is equal to n. Correct. So now you can say that so this particular factor, okay, so this particular omega cube by sorry, this is okay. There are this is in 3 dimensions, so we should write this as 3n, because that is what we used, 3n h cross omega earlier. So this is 3n. So this I can write it as so let's say this factor, that is 2 by pi ct cube plus 1 by pi cl cube. So this can be written as 9n divided by omega d the cube. So this gives us the density of modes. I can write, we can write the density of phonon modes. You can write that as G of omega is equal to, it is like 9n divided by omega d cube into omega square for omega less than omega d, less than or equal to omega d, and 0 for omega greater than omega. That means we have something like this. If you want to plot omega versus g of omega, so you see that you have a quadratic dependence. It goes like this, and then it just becomes 0 after. So this is Debye density of states. Okay, but I would like you to look at, you can actually calculate, I mean experimentally get the density of states for phonons, okay, by using experiments such as inelastic neutron scattering, things like that. And I would like you to verify what that looks like. Let me see if I can show you how it looks like. Just give me a minute. I will try to. Okay. Oh, let's see. Yeah. So I just try to give you this. So whatever this expression that I have is for some particular material. That's not very important. This number that we have here is the characteristic property of that material. I think this is for aluminum. Uh, so the point that I'm trying to make is that if you are doing an experiment, this dotted line here is the Debye. So this is Debye density of states, whatever we have written here, and the solid line is the experimental. So you can see that the theory is not quite right, or whatever Debye assumed is not quite right. It is of course at very low frequencies, it is okay, but then after that there are deviations. Not only deviations, but there are important sharp changes. That means these are called non-differentiabilities. That means this curve is not differentiable everywhere. And these differentiable, non-differentiabilities in the density of states has got an important message. I think people in solid state physics try to get some information about these things to understand the singularities have some very important things that are uh, supposed to be useful in predicting some results. Okay, so that is one thing. I think it is so that's okay. So that is I just wanted to show that the okay. So that is as far as okay, good. So now we have this density of states. So what I am showing here is a comparison between an experiment and theory. So experimental density of states has got these singularities, and these singularities have some important, and this is 0 of if omega is greater than. Now we don't have to worry too much about the nature of these lattice vibrations, because now it is like a gas of phonons, and phonons are bosons. So we can borrow all that knowledge that we have about bosons and then use them. So one of the important information that we have been using right from the beginning is that if you say that you have got uh, certain certain energy, okay, so let's say energy h bar omega. If you have this energy, then we can ask average number of phonons that have this energy. So that is given by 1 by e to the power beta h bar omega minus 1. Okay, so since of course this is correct, since mu is equal to 0, which implies the fugacity is equal to 1. Okay, so because of that, I don't have Z inverse here. It is simply 1 by e to the beta h bar omega minus 1. Okay, so this is something which this is the average. This is average occupancy of energy h bar omega. Now to find out the specific heat, we have to get the internal energy of the system, and that is basically the average energy of the system. So average energy of the system can be obtained by, so we have to get the average energy of the system. Of course, average energy in this case is easy to write down. So average energy in this case is you have h bar omega, this is the energy, and average number of particles, this will be like an average energy, but then I have to integrate this for all these frequencies. That integration is done by using this g of omega d omega, and then I integrate this from 0 to omega d, because beyond omega d, g of omega is 0 anyway. So that's my average energy, and this means, so that implies I have h bar omega, and g of omega, as I have written there, is 9n divided by omega d cube integral 0 to omega d h bar omega into omega square, that is from the g of omega, divided by e to the power beta h cross omega minus 1. Okay. So this is my E. Now you can see that this omega d is some constant, and we don't have of course d omega, correct? So this is what we have to do. Now I would probably say that we can get this, so we can simplify this a little bit by let us set beta into h cross omega as some x. Then I have omega is equal to x divided by beta h cross. Okay, and d omega is dx divided by beta h cross. Okay, so if I use this, then I can write down this average energy as 9n divided by omega d the whole cube, omega d the cube, into, I can pull out a h cross, and then this is omega cube, and there is a d omega. So that means I have 1 by beta h cross whole to the power 4, omega by beta h cross whole to the power 4, because 1 beta h cross, 1 by beta h cross from here, 1 by beta h cross square from here, and 1 by beta h cross from here. And if I have, so I can say xd can be written as beta into h cross omega d. Okay, so xd is beta omega h cross d. Now you can say that this is, I can write this as integral 0 to xd into x cube dx divided by e to the power x minus 1. Okay, so this is to some extent is what is the expression, but remember that this xd, which is the upper limit of this integral, has got this beta, which is 1 by kBt. Now let us look at this the case of a low temperature. So that means if temperature is low, T is low, okay, that means your beta is high, because beta is 1 by kBt. So for low temperature, we can say that for a given omega d, beta h cross omega d, that is your xd, can be very large. Can be very large. And let us assume that we are considering so low a temperature that this xd can be taken to infinity. Okay, so we are talking about such a low temperature that we can make this go to infinity, in which case I can say that this low temperature expression for the average energy is omega d cube into, I have kBT to the power 4 divided by h bar cube into integral 0 to infinity x cube dx divided by e to the x minus 1. Now, what is the advantage in this case is that this integral, okay, whatever is this integral is going to be some constant, right? So, the integral, there is no temperature dependence for this. So, integral is some constant, which I'm not interested in evaluating because it doesn't have any dependence on temperature or n or anything. X is something which is getting integrated out, and the limits are, they themselves are not functions of temperature any longer because we have assumed this xt to go to infinity. So it's going to be some constant. So this tells you that so this implies that this average energy, which is essentially the internal energy of our system, is so 9n by omega d the cube into kb to the power 4 by h bar cube into some constant, that is this integral. Okay, so let us call that as some I into t to the power 4. So this immediately tells us that when you want to write down your CV, which is equal to the derivative of this E with respect to t, you will get some particular all these factors into t cube. So the specific heat is proportional to t cube behavior, which is observed experimentally in experimentally observed in in the beginning, can now be derived from the Bose-Einstein statistics. Okay, so this is this is what is called Debye theory, and so it is not necessary to evaluate this integral because this integral is not going to be a function of temperature. Okay, so this is as far as the Debye theory of specific heat is concerned, and concept of phonons and the phonon population is what is used here as an application of Bose-Einstein statistics, that is in terms of using average number of particles occupying or having an energy h bar omega, is what finally gives us this expression that specific heat is proportional to TQ. Okay, so that is, I think we have covered essentially some applications of Bose-Einstein statistics. So we have done three things, that is in BE statistics. The first was we talked about Bose-Einstein condensation. And the second was we talked about the distribution of thermal radiation. Okay, so thermal, not calling it black body radiation because Bose work has removed black body, the thermal radiation distribution. Or what Niels Bohr calls as temperature radiation. And the third is the Debye theory of specific. Okay, so these are the three applications we have seen in this Bose statistics. Now, let me make some comments about some of these things. So let's say I make some remarks. First is with respect to experimental observation of Bose-Einstein condensation. So 1925 was the theoretical prediction. But the experimental BEC was done in 1995. Okay. So there is a gap of 70 years, and that is because the transition temperatures, okay, the transition temperature TC is of the order of a few nanokelvins. That is of the order of 10 to the power minus 9 kelvins. Okay, so it required these many years because you have to develop the cooling techniques. Okay, so that is a major impediment in terms of getting this. So there are two important techniques which were developed. One is called laser cooling. Normally, laser cooling is one technique, and then there is another technique called evaporative cooling. So by combining these two, people were able to achieve this kind of temperatures. Now it's interesting to see how it's very challenging to get these temperatures, because you see Bose-Einstein condensation. So one of the challenges is to you take a gas and then keep it as a gas up to nanokelvin temperatures. Okay, so that means this BEC is is a phenomena that occurs in ideal Bose gas. That means you must keep the gas as gas, because if you decrease the temperature, then the gas becomes liquid and liquid becomes solid and so on. You have to avoid that. That means you must take the gas should be so dilute that uh, so dilute and pure, because remember that if there are impurities, okay, so impurities can act as nucleation centers for phase change, and we have to avoid that. So that means we should not have, and then it has to be very dilute, because we should not have, we should have no three body collisions. Only collisions have to be binary collisions. We should not have three body collisions. So normally what happens is, if you have one object and then there is another object, they are coming and hitting each other, then they exchange their momentum and go away. So this might go away like this and this might come away like this. But if there are three particles, then these two particles can give their momentum to a third particle, and then they can stick together, and that will form a nucleation center, and one more particle can come stick to that, and so on, and then the phase change can happen again. So you must make it so dilute that we should have no three body collisions. Okay, so that is important thing. That is in starting this thing itself. Then when you are trying to cool this system, so in terms of laser cooling, so essentially the idea is that your average energy, that is your average kinetic energy of the particle, is at temperature T is given by 3 by 2 kBt. So if you can somehow decrease this energy, okay, so if you can decrease this energy, that means decrease this velocity, then you can also decrease the temperature. So that is the idea. So essentially what you do is you try to, let's say you have this particles in the gas going in all possible directions. So now you try to shine lasers in all 6 directions. Let's say shine laser in all these directions. Okay, so essentially this means that you can so if there is a particle that is coming in this direction, and there is a light which is a photon which is hitting that particle, then the particle will absorb this energy, and then it will immediately re-radiate it. But re-radiation will not happen in that direction. It will happen in some random direction. So because of that, at least the velocity in that direction will become less. But then you can also say that you can say that if a particle which is going in the opposite direction, then this fellow might also increase the velocity of that, because this is going to hit that one, and then you can say it will increase the velocity of it. So for that, what they use is they use this uh, there's this Doppler shift in the frequency. So essentially, what you do is that let's say that you have uh, something like the number of particles. Okay, so you have uh, it is something like this. I'm sure you might have seen this picture in some other context. Let's say this is your omega, and you have some kind of a spread in terms of so this is what is this? If omega is some kind of a resonance frequency of if omega is kind of a resonance frequency at which it can absorb light, and you can say that the probability that the light absorbs of the frequency omega is highest, whereas the probability that it will absorb other frequencies is also, it will decrease very fast, but there is some kind of a probability. Now what you can do is let's say that suppose if the particle is coming in this direction, okay, then there will be a frequency shift because of the Doppler effect. That means you are going to see a higher frequency of a higher resonance frequency because of this Doppler shift in the frequency. So that means we are not going to keep our laser light of this frequency, but we are going to keep the laser light of some slightly shifted frequency, so that this particular frequency you are going to have only those particles which are moving with some high velocity in this direction will absorb, and the other particles will not absorb. Okay, or their absorption is less probable. Okay, so because of that, what happens is that these particles which are moving with high velocity in this direction, they tend to absorb more photons and then re-radiate, of course, in some random direction, and thereby their velocity in this direction will become reduced. So like that, you put these lasers in all the 6 directions. This is called optical molasses. And then when you do this in all the directions, and then implement this Doppler shifted laser frequency design, and then you will see that the temperature of this will reduce, because you are actually taking the velocity of the particle to reduce in all the directions. So people were able to go up to, using this laser cooling, they are able to go uh, up to something like a few microkelvins. Okay, so but that's not enough, because you have to go up to nano Kelvin temperature, and nano Kelvin temperature can be achieved by combining this. Each of these steps which I am very qualitatively presenting took decades of experimental trials and experimental efforts. So I am only trying to give a very sketchy outline of the concepts involved in this. Then you have this evaporative cooling. Evaporative cooling as a concept is very simple. So evaporative cooling is something like when we have a very hot cup of coffee, we blow on the coffee to cool it. So the blowing on the coffee is essentially, most of the high velocity particles are on the on the top surface, and when you blow, you are actually pushing them away from the cup, so that the remaining particles are, so whatever relatively high velocity particles will come to the top layer of the cup, and then when you blow, you will actually, you are doing an evaporative cooling. So what these people did in evaporative cooling is that they used some kind of a trap. Okay, this is called MOT, magneto-optic trap. So these particles are trapped. That means it is like you are creating a potential well in which you have these particles. Okay, so if you see these particles in this potential well, they are the particles which are in this high potential region are the ones who have larger velocities. Okay, so you trap this potential in some using some magnetic field and lasers. It's called magneto-optic trap. Now you trap this, and then uh, you suddenly reduce the height of this potential well. Okay, that means you are suddenly making this potential well like this. So then what happens? All these fellows who are, all these particles who are there, they just escape. So what remains in this potential well is some low velocity particles. Okay, so and so like this you do, then you can see that the solution to these problems can be a solution to this particular so people were able to combine these two in a innovative way, and then go up to nanokelvin temperature. And when they go to nanokelvin temperature, then they find that the macroscopic occupation of the ground state could be realized. So how do they do it? They realized it. So you look at what is called a momentum space. Let's say this is your kx and ky or something like this, and then you can look at uh, you can look at, so if you are imagining this a graph like this, this is your kx and this is your ky, and then look at the population, then you will see that there is a huge population in the near zero. There is a peak, and of course there is some population here, but then this huge population in the near the origin is a signature that the Bose condensation has taken, Bose-Einstein condensation has taken place. So this is in some sense how the experimental work on this Bose-Einstein condensation has been done, and this kind of techniques were developed in the incumbent 70 years of time from the theory to experiment, and then you have finally since 1995 there are many uh, times with many systems, rubidium, all these alkali elements, people were able to show Bose-Einstein condensation. Now Bose-Einstein condensation is also a very interesting state of matter where you have it's a kind of quantum matter, in the sense you have many particles which are completely in a coherent superposition of like there is one many particle wave function which controls all the particles, and that's an interesting state of matter, and people have been trying to understand and then use these things in applications. So this is a very active area of research in terms of trying to use Bose-Einstein condensation more in theory and less in experiment. But theory, people have worked left and right on these systems and predicted so many things. Experiment is also picking up, and this is a very active area of research. Bose-Einstein condensation and the use of Bose-Einstein condensation condensates as a new state of matter in terms of various applications. Okay, so this is first remark I wanted to make. So the second remark is with respect to counting. Uh, so Bose Bose counting has got the following uh, following idea. Suppose, let's say that we have n particles in let's say m states. Okay, we have n particles and m states, and the number of ways in which these things can be arranged. Okay, so the number of arrangements. Now this particular number of arrangements, if you want to call it as some w, is given by this n plus m minus 1 factorial divided by uh, n factorial into m minus 1 factorial. Now there is there is an interesting symmetry, that is, if you alter this n going to m, suppose instead of talking about n particles in m states, I talk about m particles in n states. This w is unchanged. Okay, the w is unchanged. Now this particular fact, or this particular feature, is what I was trying to say in some earlier class, that you can actually make a transition from particle centric nature to state centric nature, because there is a kind of a symmetry between these two in this particular way of counting. So I can, instead of asking how many ways these many particles can be populated in these many states, I can simply ask what is the occupancy of this particular state. So I can simply say that, okay, I am interested in fixing the state, and then I talk about the occupancy of the state. Okay, so this is possible because this is when is this possible? This is possible only when so there is an implicit, so this implicitly means, even though he did not say this explicitly in his work, neither Einstein said it, this implicitly means that the particles are identical. If the particles are not identical, then this kind of a symmetry cannot come through, because the number of configurations will be different, and this kind of an expression is not true if you have a distinguishable particles, and hence this symmetry also is not possible. So I think this kind of a symmetry that is inherent in Bose counting method is an indication that these particles are identical. The notion of identical particles, as I told you earlier, that is a consequence of a lot of work in the next 3 to 4 years in quantum mechanics, namely 25, 26, and 27. And people like Pauli and others, Dirac, Pauli, and these people have come up with this notion of identical particles and then symmetric and antisymmetric overlaps, later determinant, etc. These things are an after uh, or yet to come during the time when Bose has done this work. And but his idea of counting uh, are shifting from particle centric to state centric is maybe he has some insight and did not communicate it in the papers, but this is something which is very original in my opinion. Okay, so this is one other remark I wanted to make. Okay, so I think yeah, okay, I think one more remark we have to make at the end. So the third
Sir,
remark, yes.
sir, can you please explain how that W is equal to n plus m minus 1 factorial by that counting? How it came? Can you give an example or something?
So I think we had used this
Correct.
earlier.
We have discussed this. That when I was studying that I had the similar doubt.
Okay, so essentially this is like uh, so the idea is something like this. You have it is like so when I say there are m states, okay, so the state is like uh, so suppose if I say that I have state m states, that means first state is with omega, sorry, h bar omega, this is the energy. Second state is with 2 h bar omega, and so on, right? So the m states is like m units of energy, which we called as units of energy, or we call that as quanta. I think we did this way back when we were doing microcanonical ensemble or the Einstein theory for microcanonical ensemble. So essentially, what do we mean by saying this kind of accounting is that I have m units of energy and I have to distribute among m particles. So I was trying to use this trick where I have. So let us try to take a simple example of let's say I have three particles, and let's say I have 4 quanta. Okay, so then the way I distribute them is that I put 2 sticks here to say that this is the energy share of particle 1, this is the energy share of particle 2, and this is the energy share of particle 3. Now I can say that I put 2 here and 2 here and nothing here. This is one particular configuration, correct? Or I put 1 here and I put 3 here and nothing here. This is another configuration. So 0, 0 and 2 here. This is another configuration. Like this I can have all possible configurations. I can enlist possible configurations as far as this is concerned. But now from this I can abstract out a formula. So what am I doing here? Essentially what I am doing is I am so different configurations are obtained by essentially sliding these n minus 1 partitions, or you can call them as sticks, two different positions. Correct? That is what we are doing. Here I have slided this from here to here. Then I got this one. Then I have slided this from here to here. Then I have got this one. Correct? So by sliding these sticks here and there, I am getting different positions. Now this mathematically implies, that how many ways can I choose these n minus 1 partitions among, now I have to choose n minus 1 partitions among the objects. What are the objects? Objects are units plus the partitions among n plus m minus 1 objects. Okay, there are m partitions and then n minus 1 partitions and m quanta. So total number of objects are this. Among them, how many ways I can choose this n minus 1, and that is my W, and that is equal to n plus m minus 1 C n minus 1. Okay, so this is what it is, and you can, so in this case there is a symmetry that I am talking about, that you change n to m or m to n, it remains the same. Okay, so this is this clear?
Yes, sir. Thank you, sir.
Okay. Now the last remark I wanted to make is this is something which I somehow probably don't remember. Maybe I have not done it in the class, but it's not very difficult to. I will leave it for you to read it for yourself, but I'm just making this remark so that you don't forget. So when you take an ideal Bose gas, so let's say you have ideal Bose gas. At very high temperature, you have ideal gas is equal to n kBT. Okay, this is your ideal gas equation of phase. So at high temperature. Now you can ask a question that so at Tc what happens? At T is equal to Tc. So you see that this PV will be n kb Tc. It's not this, but this will be something like 0.51. Okay, so it is something like, it's roughly half of the value of the ideal gas. Okay, so the equation of state at T equal to Tc or PV at T equal to Tc is half of what it will have been if it is an ideal gas. Okay, so this is one aspect. Secondly, for specific heat, okay, so this is one result. Okay, now the specific heat Cv is equal to 3 by 2 n kb. This is for high temperatures. Now what happens at T equal to Tc? At T equal to Tc, you will see that the specific heat is 3 by 2 n kb times something like 1.992 or something like that. Okay, there may be some more decimals here. Here also there may be some more decimals. But that means it is roughly 2 times the value of specific heat at ideal gas value. So these are the two things which Einstein himself in his paper had worked out. and then said that okay, the pressure is reduced. Okay, so and the specific heat has a higher value than the ideal gas value. Now you can show this because you know that we had these expressions. Okay, like you have PV by KBT is equal to RP by KBT is equal to 1 by lambda cube into G 5 by 2 of Z, and you have N, which is equal to V by lambda cube into G 3 by 2 of Z. Okay, so try to find out these expressions at T equal to Tc, because you know Tc is related to this one. Then from this you can get these results. So I will leave this kind of derive these results as an exercise, because that is instructive, and then you can verify that the pressure times volume is half the ideal gas value, and specific heat is 2 times the ideal gas value. So I would say that we have completed our kind of course on Bose-Einstein statistics, or ideal Bose gas. There is one thing which I may do at a later time, that is essentially the theory of superfluid helium, but that's not a part of our syllabus. But if there is time, then I would like to show you how liquid helium can be understood from using statistical mechanics. So from the next class, we will go to Fermi statistics, Fermi-Dirac statistics, and in the Fermi-Dirac statistics, we will essentially do I think 4 or 5 calculations. First, we will talk about electrons in metals, and then look at specific heat of electrons in metals. Then we will talk about the Pauli theory of paramagnetism, where the Fermi-Dirac statistics is applied to get some low temperature behavior of the susceptibility. And then we talk about Landau theory of diamagnetism. So Landau theory of diamagnetism is important again to understand the low temperature behavior of susceptibility. There is no classical theory, even though we have studied paramagnetism theories, but diamagnetism has no classical theory. And then we switch over to understanding the stability of white dwarf stars. And white dwarf stars are neutron stars in such celestial objects where the degenerate pressure of Fermi gas is so high that it is sufficient even to counterbalance the gravitational contraction, and thereby providing stability for billions of years to these objects, which are so faint yet so many in number in the universe. So we will try to study that as an example. So that would probably complete our list of topics in Fermi statistics, Fermi-Dirac statistics. Okay, so I will stop here, and if there are questions, please ask.